Has been working in the Marina Guenza group. And Mel, would you tell us which college you're from?
Like you said, my name is Samantha Mellin. I've been working in the Guenza group. I'm from PCC, Sylvania. What we've been doing is we are making a mesoscale simulation to accurately map the thermodynamic and dynamic properties of polymers. So mesoscale, you might be wondering, what does that mean? It means intermediate scale. Right now we have United Atom simulations that are very reliable, and they look at each. I don't know how this works. And they look at each different particle in the polymer, and they lump each monomer into a single unit, a particle. And so in the mesoscale simulation, to make it easier so that we can run longer simulations on more particles, we take each of those chains, each polyethylene chain that we want to look at for our polymer, and we use the center of mass to kind of make this estimated soft sphere. And then we run that through our simulation, which is LAMS, which is run by the San Diego National Laboratory. And after we get all that information, what I do is I look at the results and I kind of analyze them and see how they line up. So what I was looking at was density. And we were hoping, well, what we found was that all of the simulations kind of ran on the same curve. And this is a radial distribution graph. So it shows us the amount of space in between particles. So along here you have the probability of finding a particle along the y-axis, and along the x-axis you have distance. So at first you see there's a large incline. This area here is taken up by the particle, so you don't really expect to find a particle on top of another particle. But as a polymer, as you increase the distance, you have more entangling, and it eventually comes up to this one point. And at one, it actually peaks a little bit above where we've got the overlap, and then it evens out, which is indicative of a liquid, because you know that liquids have their general even space. So I looked specifically at the densities and how the density affected the simulation. And you can see everything really follows the same line. It's nice and even. We saw what we expected, which is the lower densities are a little lower, and then they all overlap, because once you get to a certain density, you can't pack a particle anymore, which was perfect. And then we compared it to the United Atom simulation, which I mentioned before is a reliable way of mapping polymers right now. It just takes a really long time compared to a mesoscale simulation. So you can see the mesoscale simulation is not only smoother, but it all kind of lines up well together, and it gives a good representation of the properties of the polymer, and it runs so much faster than the United Atom simulation. I also worked on a couple of other projects while I was working in the lab. I looked at the mean square displacement, like Morgan mentioned earlier, which is the amount of space or the amount of movement in between particles. And then I calculated the diffusion coefficient based on that, and I'll talk about it more in my poster presentation. And I also looked at polyethylene 44, which is a little bit smaller than polyethylene 66, and it showed similar properties. I looked at different cuts. When you're looking at polymers and liquids, you can see here I've got a graph of force over distance. The force peaks, and then it crosses the zero axis, and then it crosses again. So we look at both of those points to get an accurate representation of the full movement, the dynamic properties of the particle. And then I compared it to the United Atom simulation, and what we found was a really smooth graph that had good overlap with the United Atom, except instead of taking weeks to perform, it took hours. And I made a ridiculous number of graphs on Grace graph making. So I want to thank UCORE for bringing me here, and the University of Oregon for hosting us. And I'd also like to thank the Guenza group, my lab, which are over here, and would like to open up to any questions you guys might have. particles are so huge that we run them in parallel, which means we're running them a whole bunch. I actually used the San Diego supercomputer so that the simulation can run quickly and I can, be able to analyze my results instead of taking years to figure out what I want. Other questions? I'll ask Colin and then I'll go to Lucille. Colin.
Okay, so I know this is all theoretical at this point in time, but in the future, with looking at these properties of these polymers, what kind of future applications do
Thank
they
you for
have?
reminding me of that. Actually, so polymers are plastics, and you all use plastic, and it's important to understand the liquid properties of plastic. So right now we've got United Atom simulation, which allows us to predict kind of the movement and properties, but it only gives us a small time frame for polymers that are this long. And as we continue to look at longer molecules over longer time frames, this allows us to kind of predict what's going to happen. So when we're making cool new things that we want to know how they're going to work, we can map them and see them before we go into production, which is extremely helpful. Stanfield.
Okay.
Lucille. Sorry, Lucille.
I had the same question.
Oh, okay.
Okay, so we have the United Atom simulation, which we're pretty happy with,
Yes,
aside from the
very
amount of time
happy
it
with
takes.
United Atom.
Then we have the mesoscale, and your focus was densities.
We're making the mesoscale simulation. So I was looking at densities to make sure that we have a uniform results, which we did.
So other aspects been tested like this of comparing the mesoscale to the United Atom simulation?
We have, and we're actually moving, in fact, a future direction that we're kind of exploring right now is effects of temperature. We really do, we look at all kinds of things. They've really refined this simulation. It's looking really excellent right now. It was fun to go through and see how density did and did not affect the simulation. And I think you guys are kind of in the final steps, aren't you? So yes.
Yes.
I was just analyzing and making sure it was all.
So you were just making sure that they did the work right and that everything was right.
Yes, that was exactly what I did. Okay.
Question about the graph that it was like force and
The cuts.
density, or either
It was force over distance. I'll come back to it real quick.
Yeah, with the cuts, that one, where it goes below 0 and then back.
Oh, it's team time. Oh yeah. So what was?
So is it like, okay, force over distance, so is it like individual particles or chains or what have you, there's a repulsive force between them that increases with distance and then decreases with distance, and then does that mean there's an attractive force between them at a certain, or like what? Can you explain what that means?
That is an excellent question. Ask me at my poster presentation.
Okay.
Each density has a different force though as well. So in each density, I looked at the force at when it first crosses the 0 and then when it comes up again.
Is it like the force between particles?
Yes.
Okay.
So are you guys using polyethylene because you understand more about it and can kind of get a hold of using this type of analysis on it and then expand to other things?
Right now, polyethylene is pretty simple to look at. You've got each ethylene particle. We also look at proteins. They've looked at not just, I was just looking at polyethylene 66 by itself and polyethylene by itself. You can also have mixtures of different polymer amounts. But that was just in particular what I looked at.
Any other questions? No, thank you for speaking with me.